Okay, so Edexcel 2020 paper 2, and this is the higher tier. So let's go into question 1. Always need to do that first. There we go. So we've got forces on a seesaw, and it tells us at the same magnitude, and we can see that because they're the same size arrows, and it says which would be in equilibrium. So we're wanting to make sure that the clockwise and the anti-clockwise equal each other. So we just got to see which way are these turning, and are they the same distance away from the pivot. So that's turning that way. That's also turning that way. That one's garbage. Let's have a look at B. That's turning that way. This is turning this way. Yeah, it could definitely be that. That's turning that way. That's turning that way. Definitely can't be C. That's turning that way. That's turning that way. So it must be B. On to the next one, we've got an open door and the door hinges, and you'll probably remember me doing this in lesson where I put my hand, I put a student hands there, and I had my little finger there, and they pushed with all their force they could, and I could keep the door open with my little finger. And the crucial idea is we increase the mechanical advantage the further away we are, because we've got fat, moody dinosaurs. Our turning moment equals the force times the distance. So why is it easier to close the door by pushing at point P? And we can see, well, it's further away. If it's further away, I need less force, and therefore further away equals a greater turning moment. So we're just going to talk about the force, the distance, and a greater turning moment. So we can use our equation for it. So the turning moment equals the force times the perpendicular distance from the door hinge, or there we go, which is the pivot. The distance from the pivot has increased in P rather than Q, so less force is required for the same turning moment. So there we go, we've got that idea of force and distance, and we've got the idea of the pivot. Going on to the next one. So again, we've got fat, moody dinosaurs to wheedle into that. You can see I've got a little picture of that. So fat, moody dinosaurs. Remember, it's the perpendicular distance. And we've got forces on a swing. The swing is not moving, so it tells us that. So it's in equilibrium. The seat of swing AB is 0.8. So from there to there is 0.8 that we can see. A person of weight 450 sits on the seat here. The person weight acts at 0.5 from A, so we've got that there. So now we can see, well, they're the 2 bits of information we know, so I'm going to get rid of that. There we go, so that's the 2 bits of information we know, and it says ignore the weight of the seat, perfect, and the forces are equal. F1 and F2 equal each other, so we've got to find force F2. So we know that that and that are equal to each other, and it's ultimately work out this turning moment, and then that turning moment there, 0.8 times whatever this force is on F2 must equal each other, so we're away. So it's, as I said, it's use those two, and then once I've got that, divide it by that, and that will then tell me the turning moment AB. So the turning moment equals force times distance. We'll use that later. So the turning moment equals the first two we got there. 450 times 0.5 is 225 Newton meters. Then for us to work out the force that we need, F2, this one here, we're going to move that 225 across. So that's going to go here, and we're going to divide it by the distance 0.8. So now we've got 281.25 newtons, and that's question 1 done. And these always follow the same principle. Find the 2 bits of information relating to each other, calculate your turning moment, and then divide that by the other force or distance that you have.